In our second question, it is required that we find the direction of the following vectors given here. So have I and question II. Now, when we try to find the direction of a given vector, it is important for us to first identify the dimension of that vector. Because the way we get the direction of a Euclidean plane vector is not the same as the way we get a Euclidean space vector. Alright, so back to this. The first part of the question, the position vector given to us u is equal to 4i plus 4j. You know, this is the same as 4, 4 if you're writing it in scalar component form. Now, this is clearly a two-dimensional vector. Vector in Euclidean plane. And how do we obtain the direction of such vector? You would recall that we established the formula that to get the direction we need to go ahead using tan theta, which is equal to the y value divided by what? The x value. That's simply the coefficient of this direction vector j divided by the coefficient of this direction vector I. We're going to do tan theta equal to y over x, and then obtain the value of theta from there. Theta will be equal to tan inverse of y over x. So this is actually the formula that we use to obtain the direction of a two-dimensional vector. We shall substitute here directly and see what this is going to give to us. So we have 4 over 4, tan inverse of 4 over 4, which of course will give us tan inverse of 1. And what is the value of tan inverse of 1? It's going to give us a special angle. Alright? There is a right angle triangle we use for it. You can take a look. See this right angle triangle? If you do tan theta, for example, 1 over 1 is equal to 45 degrees there. So that's going to give us this special angle, 45 degrees. You can learn more about this on that tree. Is that okay? Now, this is the value of the direction of the vector. Why is that so? So I want to say something quickly. You see this vector. This vector, if you sketch it, it is in the first quadrant. How did I know about that? The coefficient of this direction vector I, which is x, is positive. Positive 4. Then that of y is also what? Positive 4. If you do the sketch, are you following right? You will notice that the vector will lie between positive x and positive y, which is the first quadrant. And as I explained when I treated the concept of the direction of two-dimensional vector, I stated that it is simply the angle that the vector makes with what? The positive x-axis measured anti-clockwise. I don't want to stress us sketching the Euclidean plane for this particular vector. Let's move on. Perhaps the second one, I will sketch it. This is quite simple. When I sketch for the second one, you'll understand. But I want to do something quickly to this. Because sometimes the angle may not be given in degree. What if the angle theta, maybe if this is an objective exam and it is given in the unit of radian, we can actually convert from degree to radian by doing theta to be equal to 45, simply multiply by pi over 180. Pi over 180 degrees. Is that okay? If you work out this, 5 can divide this, it will give us 9. If 5 goes into 180, it's going to give us, so that is actually 36. You have 9 over 36. And 9 over 36 can still reduce, you know. If 9 divide 9, it will give you 1. 9 divide 36, it's going to give you 4. So this is the same as pi over 4 radian. Is that okay? This is also another answer for this direction of this vector. Is that okay? Take note. I'll show you how to do the conversion from degree to radian. If you want to convert from radian to degree, you have to multiply by 180 over pi. Okay. Well, let's move on to the second part of the question, please. The vector given to us, the position vector r, is equal to 1, minus root 3. Again, this is two-dimensional vector. And of course, you can introduce your direction vector, specific unit vector ij to this. If you do that, you're going to get I minus root 3j. We are to obtain the direction of this vector. It's a two-dimensional vector, so theta is directly equal to tan inverse of y over x. And then if you substitute, you get tan inverse. The y value is minus root 3, but hey, I'm not going to put that minus root 3 in the calculation. I'll tell you the implication of that minus. You don't need it when calculating theta directly. Remember, angle is an absolute value. You don't have negative angle, putting a negative angle to something. So in this case, we are going to get simply root 3 divided by 1, because the value of x is 1. Alright, this is simply tan inverse of root 3. And tan inverse of root 3, again, we have a special angle for it. You can take a look at this triangle showing. So you will notice that if you do TOA in this diagram you're seeing, I thought these are just knowledge of trigonometry. So you can actually take a lesson on trig. It will help you to appreciate this. You'll notice clearly that root 3 over 1 in this diagram will give you tan 60, which means that if you take tan inverse of root 3 over 1, or simply root 3, to give you the angle 60 degrees, as you can see in this triangle that we use for this special angle, 30 and 60 degrees. So this value is simply 60 degrees. Is that okay? Now, let us look at the basis of this minus we have in this y value. Because I want to tell you clearly that this 60 degrees that we obtained in this second part of the question is not the direction of this vector. Unlike what we did here, we just got the theta and I told you that's the direction. Here, the theta we got directly is not the direction. Is that okay? In trigonometry, we learned that there are 4 quadrants in our Cartesian plane. Are you following? We have the first quadrant, the second quadrant, the third, and the fourth quadrant. Now, if I sketch this vector, watch please, let me do the sketch. Alright, so let us take this as plus 1. This is positive x-axis, this is y. And coming down, we have negative y-axis. You notice that y has negative value here. So let me just choose here as negative root 3. Alright, if you trace these two points to locate this vector that has a component 1 and minus root 3, look at where they met. Joining it to the origin, you will notice that this is in the fourth quadrant. This theta we calculated there is just this angle. Are you following, right? Theta. Okay, this is the angle we calculated. Does that make sense? This is the angle. Now, how do we get the direction of this vector? Once again, remember, direction is the angle measured from positive x-axis anti-clockwise to the line of the vector, to the vector line, to the vector itself. So this is the angle that gives us the direction actually. Is that okay? And if you look at this angle added to this theta we got, which is 60 degrees, would give us 360. That is a complete circle. So the direction of this particular vector will now be 360 minus this theta that you got. So let me write it. Theta is 60 degrees here. Minus it to get this value that we are interested in. So we can say that the direction, alright, I'm sorry that I will still use theta for it, okay? Direction of the vector will be 360 minus, you remove this one you obtained. So the remaining part. If you work on this, you are going to get, so that's the direction of this vector. Take note, this 300 degrees can still be converted to what? Radian. So let me just say R. If I want to convert to radian, I'll simply multiply the 300 by what? Pi over 180. If you do this, 0 goes off. So this is going to be 5 over 3 pi radian. So this is an alternative way of presenting the answer in radian. And that is how we obtain the direction of two-dimensional vectors. Is that okay? Very simple. Please take note. Whenever the location of the vector whose direction you are looking for, is not in the first quadrant, then the theta you calculate first is not the actual direction of that vector. You need to use the technicality of the concept of first, second, and third, fourth quadrant. Here we have any angle you calculate for a vector in this first quadrant, that's the value of the direction. In this second quadrant, any theta you calculate to get the real direction to be 180 minus the angle, the theta that you calculated using tan inverse of y over x. And then in the third quadrant, any angle you calculate for a vector in the third quadrant, to get the actual direction of the vector, you will do 180 plus that angle theta that you calculated using tan inverse of y over x. And of course, we have handled that in the fourth quadrant. If the vector is in the fourth quadrant, any theta, any angle you calculate using tan inverse of y over x is not the actual direction of the vector. In the fourth quadrant, you would have to subtract that angle value you obtain from 360. What is left would be the actual direction of the vector in the fourth quadrant. You can now appreciate and see the reason why I didn't bother you for the first part of the question, because the theta we got is directly the direction of that vector given to us in I part of this question. Alright, let us move on to our third question. Let us now look at what we have in question 3. Good. Let V equals bracket minus 1, 5, minus 2. We are to find the unit vector in the direction of V. So this vector given to us is the position vector. You can see the component there. If we like, we can write it in terms of V equal to minus I plus 5j minus 2k. That's introducing our specific unit vector, ijk, which helps us to introduce plus between these terms, alright? Okay, we are to find the unit vector in the direction of this position vector. During the course of our class, we established the formula for calculating the unit vector as cap that vector equal to the position vector divided by the magnitude of that particular position vector. Please let me say this. Magnitude is the same as modulus. So an examiner may use that word for you. When you are given something to find magnitude, you might just be told, find modulus of that vector. It's the same thing. Magnitude and modulus is the same as the length, the size of that vector. Alright, having said that, the formula for calculating our unit vector is cap V this time around, okay? When I was establishing the formula, I used U. It doesn't matter. Whatever alphabet given to you, you go with that. So, unit vector V equal to position vector V divided by the modulus or the magnitude, however I want to call it, of that vector. So you see, we need the modulus of the vector. We need the magnitude of the vector. Modulus, magnitude, the same thing. So I'm going to use any one of them. The position vector, we know it already. Look at it. Is that okay? So let us quickly go and calculate the modulus of the vector V. That is square root of x squared plus y squared plus z squared in 3 dimensions. You know that. This is a vector in Euclidean space. 3-dimensional vector. So this is going to be the formula for calculating this denominator. If we do this, this is simply square root. Our x is minus 1. But I'm not going to put that minus while solving for this. I've told you the reason for that. The square will kick it off. Or simply if you're calculating modulus, magnitude is simply positive value you want to get. So this is simply 1 squared plus 5 squared plus, I've got 2 squared. If you work out this, let's see what we're going to get. This is 1, this will give us 25, this will give us 4. 25 plus 4, 29, plus 1, 30. So this is root 30. So if you look at this 30, there is no perfect square in 30. Therefore, we can't break this down any further using the knowledge of surd. This is clearly the magnitude of the position vector V given to us. Having obtained this magnitude, this modulus, we can now substitute into this formula, this unit vector formula. Is that okay? So that the unit vector will now become the position vector, which is given to us, minus 1, 5, and minus 2. Going to enclose it in bracket and divided by the modulus of that vector, which is root 30 we obtain. So this is simply our answer. Now, if it is an objective case, there are different ways that an examiner may choose to leave the option. So let me give you the various ways that the answer can be presented. But we have already obtained the unit vector in the direction of this vector given to us. This is the answer. What I just want to do now is simply showing you other ways we can write this answer. Now, I can distribute this root 30 to each of them, and then we'll have negative 1 over root 30, and then 5 over root 30, and then minus 2 over root 30. Good. Now, we can also choose to present the answer in this format. Unit vector v. Now, since all the denominators, each of them is root 30, I can factorize that root 30 out. Pulling it out, it will come as 1 over root 30. And then I will enclose the numerator in brackets, just exactly the way it was given to us in the question. Good. There's another way the answer can be presented, or in the final form in which one may choose to present the answer is writing this thing in added form. And you can only do that using our specific unit vectors. Are you following, right? In 3 dimensions, because this is a 3-dimensional problem. In that case, I think I'll come over here. This is the x value. I'm going to multiply this x value by unit vector I. So have minus 1 over 30, then multiply by I. This is positive 5 over root 30, so it's going to be plus 5 over root 30. This time around, this is the y value. And the unit vector in y direction is j. And then finally, this is minus 2 over root 30. So this is plus minus. Of course, the minus will come in. 2 over root 30, which will be multiplied by k, because this is the z value. And k is the unit vector in z direction. So these are various ways that this answer can be presented. Each of this is the unit vector in the direction of this given position vector. Quite simple, right? Good. Now we are done with how to deal with problems involving calculating the magnitude or the modulus of a vector. We are done with dealing with how to obtain the direction of a 2-dimensional vector in Euclidean plane. And now we are done with how to determine the unit vector of any given vector. Let me also say this quickly, good enough that I just remember. What we've done here, see this formula, dividing a non-zero vector. Dividing a non-zero vector, because this is not all zeros. If this were to be 0, 0, 0, we can say that this vector is a zero vector. But this is not a zero vector. This formula you are seeing here, which is simply dividing a non-zero vector by the magnitude, the modulus of that vector itself, is also called normalizing of vector. So if I come to you and give you a vector like this one, I say normalize the vector. It's simply for you to obtain the unit vector. Divide that vector given, the position vector, by the modulus, the magnitude of the vector. Now, when we treated the direction of 2-dimensional vector, we obtained an angle which we use to represent the direction theta. I want you to go back, watch that part of the question. I think question number 2, that angle is very important to us, because I am going to teach you in just one of our fun class the polar form of 2-dimensional vectors. Is that okay? The polar form of 2-dimensional vectors. We're going to treat that, and so I need you to understand what I did when we treated getting the direction of 2-dimensional vectors. This is good. In our next class, I'll be teaching you algebra of vectors. We're going to look at how to add and subtract vectors and how to multiply a vector by another vector. Even the concept of using scalar to multiply them. Is that okay? I know you might be wondering, what about the division of vector by vector? Don't worry. in that next class, you will learn more about the things you need to know about that. I hope to see you in our next class. Until then, make sure that you take these video lessons. If you have any question, you can always ask your question. Below this video lesson, we've got quiz on it. Take the quiz and see how far you understand what have been covered so far in this topic.